Hello again, everyone. Today we're going to discuss about enthalpy. It's a very cozy word, but I'm going to give you what the definition of enthalpy means. Enthalpy in most literature is represented by delta H. Enthalpy is a flow in the process that occurs under constant pressure. It's a flow of heat, basically. It's about heat. Enthalpy is a flow of heat which occurs under a constant pressure. So one of the things we discussed about heat is about enthalpy. Why we are interested about enthalpy is that most reactions that we do in the laboratory is under a constant pressure, a pressure that's in the lab. So any reactions that takes place is considered as in a standard pressure. So when we are dealing with that, we better define the conversion of heat from system to surrounding as a form of enthalpy. My goal today is about how do we calculate, how do we relate chemical equations in enthalpy. One thing that I would like to say is that most of the chemical reactions experimentally, when they generate heat, their enthalpy value is known. But sometimes you will be asked to calculate the enthalpy change from the chemical equation. So this is one of the things that we are talking about, or chemists talk about thermochemistry. Thermochemistry is related with chemical reaction with heat. Any chemical reaction, in most cases, they produce or generate heat. If they generate heat, we call it exothermic reaction. Exothermic reaction means that when you have a chemical reaction, let's say A plus B provide you C, and some amount of energy will be evolved. So that's called exothermic reaction. Whereas sometimes some reactions absorb heat. Let's say if this is surrounding or the outside, if this is the inside, we call it system. If the system provides heat to the outside, to the surrounding, that's called exothermic reaction. And we have a situation that the surrounding will provide heat to the system, and the system will absorb heat. So in that case, the internal energy of the system will be increased, and that will lead us something called endothermic. Endothermic always be identified as a positive value. It is a sign convention that you will have endothermic, which is positive, the system gets heat. We have exothermic. Exothermic when the system loses heat. So when I say heat, I'm talking about enthalpy. Remember that enthalpy is a flow of heat that occurs under a constant pressure. So we're going to do some kind of calculation how we can able to measure enthalpy from a chemical reaction. So let's say that I can give you an example here. When a student mixes 60 milliliter of 2.0 molarity of hydrochloric acid and same amount of volume, which is 60 milliliter of 2.0 molarity of sodium hydroxide in a coffee cup calorimeter. I'm going to explain why we need coffee cup calorimeter here later on. Temperature of the resulting solution increases from I will add a number, say for example increases from 19 Celsius to 28 Celsius. Now we are okay, let's say this, calculate the enthalpy change. What would be the enthalpy change? Calculate the enthalpy change for the reaction, for the whole reaction, in kilojoules per mole of hydrochloric acid. Okay, so this is a multi-step questions. We have a chemical reaction, which is hydrochloric acid react with sodium hydroxide. Normally such reaction is considered as a neutralization reaction, but this is not simply a neutralization reaction. This is a thermochemical equation. I would say thermochemical equation because it produces some heat. So we are interested to calculate how much heat or how much enthalpy is formed. That's one question. And also we are interested to find the enthalpy change for hydrochloric acid. What would be the contribution of hydrochloric acid in terms of heat transformation for the whole process of the reaction? The given values that we have is we have 2.0 molarity of hydrochloric acid. That's the concentration. We have the volume, which is 60 milliliter. 60 milliliter is going to be, if you want to change 60 milliliter into liter, it's going to be about 0.06 liter. Let's see about sodium hydroxide. Or for the sodium hydroxide end, we have 2 molarity of sodium hydroxide, and we also have 60 milliliter of sodium hydroxide, which is 0.06 liter. This is given value, and then based on this, we're going to calculate how much heat that this reaction will generate. Now, this is a neutralization reaction. However, this is also a thermochemical equation. I would like to say thermochemical equation. The reason why I say thermochemical equation, because it's not neutralization, it also generates heat here. So I would like to know how much heat it produces. So, one of the things that we need to know here is that for any reaction, we have to calculate the amount of heat produced or generated, or the amount of heat absorbed. There is a formula for that. I'm going to use a big Q. A big Q refers that heat lost or heat gain by substance can be calculated as mass times specific heat times delta T. M refers to mass. C means specific heat capacity, whereas delta T is a difference in temperature. So basically, in our case, we have hydrochloric acid plus sodium hydroxide provides us sodium chloride and water. So we have 2.0 molarity of hydrochloric acid with 0.06 liter. Same time, we have 2.0 molarity of NaOH with 0.06 liter, and we wanted to know the delta H value. So the delta H value can be calculated as M times C times delta T. We also need to know about the mass of the solution. That's very interesting here. Mass of the solution. Remember that this is an aqueous solution. Aqueous solution. So in aqueous solution, water is a solvent. So we're going to take the density of water because this is a very diluted solution. So the density of water can be equals to the density of the solution. So the density of water is 1.0 gram per milliliter. So the total volume we have here when hydrochloric acid and sodium hydroxide reacts is going to be 60 plus 60, that provide us 120 milliliters. This is the total volume of solution. So we have density is mass over volume, total volume. I use VT. So from here, the mass of the solution, I'm going to use S. MS refers mass of the total solution. That's going to be the density, which is 1.00 gram per milliliter, times the volume of the total solution will be 120 milliliter. So that's going to be 1.00 gram by 120. That's going to be 120 gram, right? That's going to be 120 grams. That's the total solution. So we have the mass. We also have specific heat. We use the specific heat for water. Remember that this solution is pretty much dominated by water, so we use the specific heat of water as the specific heat of the solution. That is going to be 4.18 joules per gram degree centigrade. Okay, so okay, one thing that's left is delta T. Delta T is the difference in temperature, which is the final temperature minus the initial temperature. So in this case, that's going to be the final temperature is 28 degrees centigrade minus 19 degrees centigrade. So if you subtract 19 from 28, that gives us 9 Celsius, 9 degrees Celsius. Okay. So now we can go back to the formula. Like I said, delta H is going to be M times C times delta T. We all have all the value. The mass is 120 grams. The specific heat capacity is 4.18 joules per gram degree centigrade. And the difference in temperature is 9 degrees centigrade. So the unwanted unit will be crossed out here, and gram is being crossed out by gram. So we have 120 times 4.18 times 9. That gives us, if you multiply 120 by 4.18 times 9, basically it gives you about 4,514, approximately 0.4 joules. You can write this in terms of kilojoules. If you like to, in terms of kilojoules, you divide this by 1000. If you divide this by 1000, that gives you, I believe, 4.514 kilojoules. I think it's the best way, it's the easiest way to write it in joules. 4.514 kilojoules would be good. So this is the total amount of energy that is produced when hydrochloric acid, 2.0 molar of hydrochloric acid, react with 2.0 molar of NaOH, and it produces sodium chloride and water, and it also generates minus 4.514 kilojoules. The reason why I put a minus sign, it is an indication for exothermic reaction. Exothermic reaction. Now we haven't completed the whole process here. We also need to know, we wanted to know the enthalpy change for the reaction for hydrochloric acid. So the enthalpy change for hydrochloric acid, simply for hydrochloric acid, in kilojoules per mole. So how do we do that? To find out the enthalpy change for hydrochloric acid, we need to guess total amount of heat, which is delta H value divided by the mole of hydrochloric acid. The mole of hydrochloric acid. And the delta H value is actually minus 4.15 kilojoules. But we still have to calculate the mole of hydrochloric acid. So how do we calculate the mole of hydrochloric acid from this reaction? So the mole of hydrochloric acid is going to be the molarity of hydrochloric acid times the volume of hydrochloric acid. So the molarity of hydrochloric acid was 2.0 molarity that was given, and the volume of hydrochloric acid is going to be it was 120 milliliter, but we can change that into liter. It's 0.06 liter. So when you multiply 2 times 0.06, that would give you about approximately 0.12 mole of hydrochloric acid. So the enthalpy change for hydrochloric acid would be delta H for hydrochloric acid is going to be the total heat, total enthalpy, divided by the mole of hydrochloric acid. Now the total enthalpy that we had was minus 4 point, in the previous one, that's going to be minus 4.514 kilojoules over the moles of enthalpy would be 0.12 mole. So if you divide 4.514 kilojoules per 0.12, if you divide 4.514 divided by 0.12, that would give you, let me do my calculation, 4.514 divided by 0.12. That would give you about 37.58 kilojoules per mole. Okay, so the contribution of hydrochloric acid in the whole process is 37.58 kilojoules per mole. That's for hydrochloric acid. If you want to do for sodium hydroxide, you will do on the same way. So this is just one way that we can calculate the enthalpy change. And on the next video, I'm going to show you the other way around how to calculate enthalpy. Enthalpy is an extensive property. Enthalpy can be calculated in various ways, but this is just one way. Thank you very much, and I'll see you on the next video related with enthalpy and other related factor. Thank you. So please don't forget to leave a comment in a comment section, and at the same time don't forget to share and like us. Thank you.